It is a great pleasure for me to introduce our keynote speaker. I am Dr. Sunil Kumar Yadav. On behalf of Poornima College of Engineering, welcome you all in today's international webinar. Dr. Yildirim is an associate professor in mathematics in the Department of Mathematics, Kota Gazi Mapapasha University, Turkey since 2010. His research His area of research is geometry of C-alpha manifold, submanifold, Ricci-Soliton, Yamabe solution, and general theory of relativity. Besides this, Sir has credit of three books of differential geometry and its application. Currently, Dr. Yildirim working as a director and head of department IRBA Vocational School, Turkey. Without taking much more time, I am handed over the session to Dr. Yildirim. I would like to invite Professor Mahesh Bundele, Director Principal, Poornima College of Engineering, to address the webinar.
I welcome Dr. ÜMİT, who has accepted to deliver a talk on that very topic is unknown to me. Some alpha I could not understand. Actually, I'd like to understand what the topic is exactly. But I would like to thank him for accepting to deliver a talk for our students, and so it's very pleasure for us to listen to you.
I say hello to everyone and offer my respect. My name is ÜMİT Yildirim. I meet with you in Turkey. I continue my research at Tokat Gazi Paşa University Department of Mathematics. First of all, I would like to thank Poornima College of Engineering and my dear friend and Sunil Kumar Yadav that I worked with. First of all, I will talk about the using areas of differential geometry and manifolds in technology. Differential geometry is a mathematical discipline that uses the technique of differential calculus, integral calculus, linear algebra, and multilinear algebra to study problems in geometry. The theory of plane and space, surface and surface in the three-dimensional Euclidean space form the basis for development of differential geometry during the 18th century and 19th century. This discipline is based on the properties of the manifolds, where derivative is defined and metric on these manifolds deal with the concept. Riemannian geometry is a sub-branch. Differential geometry is generalization Euclidean geometry. On the other hand, differential geometry is a language in which Einstein's general theory of relativity is expressed. A manifold is local Euclidean space. Here is an example to visually a manifold. A small ant. In the picnic area, we'll see the areas where it collects picnic remains flat. However, someone looking at this view from a height will actually see that the area is curved. So it is locally flat. Similarly, the shipper is a two-dimensional Euclidean plane local and is a two-dimensional manifold. Under some conditions, a Riemannian manifold can be considered a subset of Euclidean space, which is called the embedding of the Riemann manifold in Euclidean space. Structural tools of Euclidean space can be reduced to the manifold with the help of Riemannian metric. Manifolds allows to make geometry independent of metric and even topology. What is manifold? A vector space is a manifold. A curve is a manifold, one-dimensional manifold. The set of lines passing through the origin is a manifold. In other words, projective space. The list can be expanded. What is interesting here is that all of these manifolds have their own unique geometry. What does this mean? What does the shortest distance between the 2 points indicate geometrical? If you ask, you will say line. Why? Because you see everything with Euclidean geometry. However, the geometric mean of the shortest distance between 2 points on the shipper is the large circles of the shipper. So the shipper is also big circles. The lines of a manifold called geodesics. Repeat, the lines of a manifold are called geodesics. What is the line Euclidean space is geodesic on the manifold? In Euclidean geometry, we express all shapes and generally geometric objects with the help of verifying. For example, we can get a triangle with 3 lines of which 2 are not parallel. We can think of the sine media in the manifold. Of course, in this case, very important difference arises. The sum of the angles of the triangle might differ from 108. Here is the non-Euclidean geometry. Gauss is the founder of differential geometry, and I think he is the first creator of the manifold concept. So, is there a manifold that comes out strongly in nature? Definitely yes. Let's take a look at manifold application together. General relativity, Albert Einstein published the special relativity in 1905. Einstein had been thinking about this theory for a long time and was working, but strong math essentials were needed. More was needed. Here is the Riemannian geometry that Einstein had referred to. This equation, the Einstein-False equation, ekran paylaşım yapamıyoruz ama neyse, şimdi değil. The manifold that provides this equation is called the Einstein manifold. Understanding this curvature is essential for the position of stellities into orbit around the Earth. Differential geometry is also indispensable in the study of gravitational lensing and black holes. Einstein manifolds are an area where differential geometry also works extensively. The use of manifolds in computer science. Manifolds are used effectively in imaging processing. New CNN methods have been developed by making use of manifolds and structure on deep learning. Manifold learning is data processing method in which data mining methods are performed at high level. It has been growing rapidly in recent years. In physics, differential geometry has many applications, including differential forms are used in the study electromagnetism. Differential geometry has application to both Lagrange mechanics and Hamilton mechanics. Symplectic manifolds in particular can be used to study Hamilton systems. Riemannian geometry and contact geometry have been used to construct the formalism of geometro-thermodynamics, which has found application in classical equilibrium thermodynamics. In chemistry and biophysics, when modeling cell membrane structure under varying pressure. In economics, differential geometry has application to the field of econometrics. Geometric modeling, including combining graphics and computer-aided geometric design, draw on ideas from differential geometry. In engineering, differential geometry can be applied to solve problems in digital signal processing. In control theory, differential geometry can be used to analyze nonlinear control systems, particularly geometric control. In probability statistics and information theory, one can interpret various structures as Riemann manifolds, which yields the field of information geometry, particularly with the Fisher information matrix. In structural geology, differential geometry is used to analyze and describe geologic structures. In computer vision, differential geometry is used to analyze shapes. In image processing, differential geometry is used to process and analyze data on non-flat surface. Gregory Perelman's proof of the Poincaré conjectures using the techniques of Ricci-Fullows demonstrated the power of differential geometric approach to questions in topology, and it highlighted the important role played by its analytic methods. In wired communication, Grassmann manifolds are used for beamforming techniques in multiple antenna systems. Differential geometry has many applications that do not end with counting. Now, let's talk about the main topic of seminar. Almost complex manifolds. Ekran paylaşım yapacağım. Almost C-alpha manifolds and their classification. C-alpha manifold is a subclass of almost contact metric manifolds and general case of Köhler'in, Kenmatsu, and Sasakian manifolds. Although there have been many studies on Köhler, Sasakian, Kenmatsu manifolds, the subject C-alpha manifolds has been studied very little. What is C-alpha manifolds? Let M be a real 2 and plus 1 dimensional C manifolds, C infinite manifolds, and almost co-complex structure on M is defined by a C infinity tensor file phi, C infinity vector file C, and C infinity one form eta on M such that for any point X in M, we have equation 1. Phi square X equal minus X plus eta X Xi and eta Xi equal 1. Manifold equipped with an almost co-complex structure are called almost co-complex or almost contact manifolds. A Riemannian manifold and with metric tensor G and with an almost co-complex structure phi Xi eta such that equation 2 is an almost co-Hermitian or almost contact metric manifold. The Sasakian form, in other words, or fundamental 2 form, big phi of an almost co-Hermitian manifold mg phi Xi eta is defined by equation 3. Big xy equal g x phi y for all xy in Gm, and this form satisfies eta big phi square and neg not equal 0. This means that every almost co-Hermitian manifold is orientable and that eta phi big phi defines an almost co-symplectic structure on M. If this associated structure is co-symplectic, M is called an almost co-Kehlerian manifold. When phi equal d eta, the associated almost co-symplectic structure is contact structure and M is an almost Sasakian manifold. It is known that conversely, every contact manifold has an almost Sasakian structure. Very important, this Nijenius tensor. The Nijenius tensor equation is 4 equation. Where is Lie bracket xy in Gm? On almost structure is called integrable if phi Lie bracket equal 0 and normal if phi comma phi plus 2d eta o times Xi equal 0. An integrable almost co-complex structure is a co-complex structure. This is important. In an integrable almost co-complex structure is a co-complex structure. A co-Kehler manifold or normal co-symplectic manifold is integrable or equivalent and normal almost Kehler manifold, while a Sasakian manifold is a normal almost Sasakian manifold. Let Mg phi Xi eta be an almost co-Hermitian manifold with Riemannian connection nabla. then equation 5 holds M is co-Keplerian if and only if nabla phi equals 0. M is Sasakian manifold if and only if equation 6 nabla x phi y equal g x y c minus eta y x. M is a Komatsu manifold if and only if equation 7 nabla x phi y equals g phi x y c minus eta x phi x. This this is C alpha manifold classification called. The Riemannian curvature tensor R on this manifold satisfies some interesting identities which play an important role in the decomposition theory. Let R be the Riemannian curvature tensor on M and Y, X, Y, Z, W in Km. We have equation 8. Riemannian curvature tensor X, Y, Z, W equal R, X, Y, phi Z, phi W for co-Keplerian manifold. For M Sasakian manifold, R, X, Y, Z, W hold equation 9. For a Komatsu manifold M, equation 10. This difference you see equations. Definition: C alpha manifolds. An almost C alpha manifold M is an almost cohermitian manifold such that the Riemannian curvature tensor satisfies the following property: alpha in R such that for all X, Y, Z, W in Km. Equation 11. R, X, Y, Z, W equal R, X, Y, P, Z, phi W plus alpha minus G, X, Z, G, Y, W plus G, X, W. Equation 11. A normal almost C alpha manifold is a C alpha manifold. This is important. I repeat, a normal almost C alpha manifold is a C alpha manifold. Co-Keplerian, Sasakian, and Komatsu manifolds are respectively C0, C1, and C minus 1 manifolds. C0 co-Keplerian, C1 Sasakian, C minus 1 Komatsu manifolds. Moreover, if such a manifold has constant phi sectional curvature equal to C, then its curvature tensor is given by equation 12. This C is phi sectional curvature. This equation alpha equal 0, the manifold is reduced to co-Keplerian. Alpha equal to 1, the manifold reduced to Sasakian. Alpha equal minus 1, this equation, then manifold is reduced to Komatsu manifold. This equation classification is C alpha manifold. Here C alpha manifold example. We found this example. Let us consider a 5-dimensional manifold M, x1, x2, x3, x4, x5 in R square 5. Here x2 not equal 0, x3 not equal 0, where our standard coordinates in R square 5, taking in the vectors a1, a2, a3, a4, a5. This a5 is kısi, orthogonal kısi. Let G be the Riemannian metric on M defined by G A E E G E not equal G for 0, E equal G for 1. We define the phi and B form, one form eta as phi E1 equal E2. Similarly, other tensors. It is easy to see that eta xi, in other words, E5 equal 1. Phi square x equal minus x plus eta x E5. G phi x phi y equal G phi G x y minus eta x eta y for any x y in Qm. Thus, M phi xi eta G is almost contact metric manifolds. By direct calculation, Lie bracket is we have this equations, other Lie bracket results. By using causal formula, we can easily do to find that nabla E1 equal this equation. Other similarly calculations. These other similarly calculations. By R, we denote the Riemannian curvature tensor of M. It can be easily to see that R E1, E2, E1, this equation, two equations. Similarly, this found easily calculations. These equations, Riemannian curvature tensor results. On the other hand, by using properties the Ricci tensor, we get as E1 equal to equations. This example, very hard to examples. By using the properties Ricci tensor, we can easily to find that this equation. This is scalar curvature function. Since the CFO manifold has a general structure, it is a little difficult to give an example. Since the Koch-Kehlerian, Sasakian, and Kamatsu manifold are special cases of CFO manifold, it is possible to give example by using less mathematical operations. Now, let's get to know the curvature tensor used to study the structure on the manifolds. Now, let's get to know the curvature tensor used to study the structure on manifolds. The concept of the quasi-conformal curvature tensor was defined by Yano and Sawaki. Quasi-conformal curvature tensor of a 2 and plus 1 dimensional Riemannian manifold is defined as equation this y tilde c x y z equal a r x y z plus b s s. This equation a and b arbitrary constants. Q is Ricci operator, C is Ricci tensor, R is scalar curvature of manifold. This is important. If tilde s equals 0, then manifold is said to be quasi-conformal flat. Similarly, this tensor is called a conformal curvature tensor. Similarly, if C equals 0, then manifold is said to be conformal flat. Also, taking equation quasi-conformal flat, in equation quasi-conformal flat tensor, quasi-conformal curvature tensor, A equal 1 and B equal -1 divide 3 and -1. The quasi-conformal curvature tensor reduced to conformal curvature tensor. Here is C denotes the conformal curvature tensor of manifold. Let M be 2 plus 1 dimensional Riemannian manifold. The projective curvature tensor field is defined by equation this. P x y z equal R x y z -1 divide 2 and S y z x minus S x z y. Similarly, if this P equal 0 is called the manifold is projective flat. Let M be 1 plus 1 dimensional Riemannian manifold. The consensual curvature tensor field is defined by tilde z x y z equal R x y z minus R divide 2 and plus 1 g y z x minus g y x z y. Similarly, if this equation equal to 0, then it is a consensual flat. Manifold is consensual flat. Other curvature tensor. Schumann defined a tensor field B on an n-dimensional Riemannian manifold M squared and G as this equation. This equation is the conformal curvature tensor. According to me, this very important curvature tensor. Such a tensor field B is known as the conformal curvature tensor, where is the constant K R plus 2 and -1 divide n minus 2. R is Riemann curvature tensor, Q is the Ricci operator, C is the Ricci tensor, and R is scalar curvature of M. There are so many tensors we can't write here. Perhaps someone might have identified another curvature tensor right now, but I want to draw your attention to something. Almost all tensors consist of a combination of Riemannian curvature tensor R, Ricci tensor S, and Ricci operator Q. This is very important. It contains several other constants and some function. To me, this means that if we apply special condition to C-alpha manifolds, then these C-alpha manifolds must be reduced to a more specific station. For example, real space form Einstein manifold some spatial symmetric state. Many articles about this have been studied for so far. I also have studies on this subject. Some of the results I got from the work I did for this area as follows. These theorems I found in my doctoral thesis. Theorem. Let M be a 2 and plus 1 dimensional and almost C-alpha manifold, then is a semi-symmetric if and only if M is of alpha sectional curvature. New theorem. Let M be a 2 and plus 1 dimensional and almost C alpha manifold. If M is projective semisymmetric, then M reduced to an Einstein manifold. This, your attention, alpha sectional curvature M is and N reduced to Einstein manifolds. New theorem, let M be N2 n plus 1 dimensional and C alpha manifolds, almost C alpha manifolds, then M is quasi-conformal semisymmetric if and only if M is of alpha sectional curvature. New theorem, let M be a 2 1 plus 1 2n plus 1 dimensional and almost C alpha manifolds, then tilde C x y are equal 0 if and only if M is either alpha sectional curvature or the quasi-conformal curvature tensor reduced to conformal curvature tensor, provided that alpha minus C not equal 0. New theorem, let M be a 2n plus 1 dimensional and almost C alpha manifolds, then M is quasi-conformal flat if and only if it is either a conformal flat or it is of alpha sectional curvature. Sorry. Let M be 2n plus 1 dimensional and almost C alpha manifolds. M is consortular semisymmetric if and only if M is isometric space, projective, hyperbolic, and Euclidean with respect to these conditions. New theorem, let M be 2n plus 1 dimensional and almost C alpha manifolds. M is Riesz semisymmetric if and only if M is an Einstein manifold. New theorem, let M be 2n plus 1 dimensional and C alpha manifolds, then M is local phi symmetric if and only if M has alpha sectional curvature. Similarly, M is local symmetric if M has alpha sectional curvature. New theorem, every and almost C alpha manifold M is always eta parallel. Corollary, an almost C alpha manifold is always an eta Einstein manifold. New theorem, let M be 2n plus 1 dimensional and almost C alpha manifold, then tilde S tilde C Xi X Z equal 0 if and only if M reduce a real space form with constant sectional curvature C. New theorem, let M be 2n plus 1 dimensional and almost C alpha manifolds, then tilde C Xi X P equal 0 if and only if M has either alpha sectional curvature or it is an Einstein manifold. Let M be 2n plus 1 dimensional and almost C alpha manifolds, then tilde C Xi X S equal 0. This S is Riesz tensor if and only if M is an Einstein manifold, provided that E plus B multiply 2 and minus 1 not equal 0. New theorem, let M be 2n plus 1 dimension and almost C alpha manifold, then tilde Z Xi X tilde C equal 0 if and only if M either is a real space form with sectional curvature C or the scalar curvature R equal 2 and alpha multiply 2 and plus 1. Theorem, let M be 2 and plus 1 dimensional and almost C alpha manifolds, then P Xi X are equal 0 if and only if M reduce a real space form with constant sectional curvature C. Let M be 2 and plus one dimensional and manifold, almost C-alpha manifolds, then P x tilde z equals 0 if and only if M is a real space form with sectional curvature C. Let M be 2, 1 plus 2 and plus 1 dimensional and almost C-alpha manifolds, then P y tilde C equals 0 if and only if M has either alpha sectional curvature or it is an Einstein manifold. It seems that all the results I found so far have actually been reduced to a few exceptions. However, we still have not been able to find what is important to use. A C-alpha manifold is reduced to Koch-Kehlerian, Sasakian, and Komatsu manifolds under which spatial conditions using which curvature tensor. For this station, it was necessary to apply another conditions or another curvature tensor. In a 2 and plus 1 dimension almost C-alpha manifold, the following relations are satisfied. Equation R xi yz equal alpha g yz xi eta zy. The equations similarly we found. This equation R is Riemannian curvature tensor. Tilde z is tilde z is conservative curvature tensor. P is projective curvature tensor. Olabilir. B is bir saniye. Bir şey söyleyeyim. Ayaklarım üşüdü de klima şey var mı? Kapatsak iyi olur. B is yz xi equal alpha plus 1, this is important, alpha plus 1 divide 1 minus n eta zy minus eta yz. And equation 32. B xi yz equals this equation. Also, we can state the Ricci tensor properties, use of the Ricci tensor properties. We obtain as xy equal this equation. C-alpha manifold is Ricci tensor, this, which is equivalent to Ricci operator formula this. Corollary, an almost C-alpha manifold is always an eta Einstein manifold. This corollary repeats. Also from 2-7 equation, we can easily see scalar curvature function, this equation, R equal an alpha 3 n plus 1 plus C n plus 1 and S x xi equal 2 n alpha eta x. This years to equations 31. Theorem. Let M be 2n plus 1 dimension and C-alpha manifolds, then M is the conformal flat if and only if M reduce a Komatsu manifolds. This very important results, according to me. C-alpha manifolds reduced to before projective real space form, not projective, real space form, Einstein manifolds, phi sectional curvature C is like. And this theorem, M is the conformal flat if and only if M reduce a Kenmatsu manifold. C alpha manifolds, general case Kenmatsu, Köhler, Sasakian manifolds, this theorem reduce a Kenmatsu manifold. Proof. Let an almost C alpha manifolds M be a D-conformal flat for X, Y, Z in Qm. Then we have D-conformal flat is Bx, Y, Z equals 0. Similarly, projective flat, concertular flat, quasi-conformal flat, like. In equation, choosing Z equal C, we obtain this equation by direct calculation. We conclude that alpha plus 1 divides n minus 1 equals 0. So for alpha equal alpha equal minus 1, M is an C plus C minus 1 Kenmatsu manifold. This C alpha manifolds reduce to Kenmatsu manifold. Let M be 2n plus 1 dimensional and almost C alpha manifolds, then M is D-conformal semi-symmetric if and only if M either reduce a Kenmatsu manifold or it is a Köhler manifold. This very important theorem, C alpha manifolds reduce to Kenmatsu manifolds or Köhler manifolds. Proof, we suppose that 2n plus 1 dimensional manifold, almost C alpha manifolds M is D-conformal semi-symmetric. Then have been the symmetric conditions is R X Y B equals 0. This name, this called D-conformal semi-symmetric. This B is P projective. This name is projective semi-symmetric. This B is Z. This name is, this called is concertular semi-symmetric. Like from 3,6 we obtain this equation. This equation choosing X equal X equal C, and using the equation 18 we obtain this equation. Now putting this equation and using equation, this double question is, we found it before, please. Double question is, we found before it equation. In the same way, choosing Z equal C in and using equation, we conclude this 40 equation. Very important. Alpha multiply alpha plus 1 divide n minus 1 equals 0. So M either reduce a Komatsu manifold alpha equal -1 or it is a Köhler manifold alpha equal 0. The converse is trivial, the proof is complete. Let M be 2n plus 1 dimensional and almost CFA manifolds, then B is the D-conformal curvature tensor, B xi y tilde z equals 0 if and only if M either reduce a Komatsu manifold or real space form with constant sectional curvature. C equal 2 alpha minus R divide n 2n plus 1. Where is the reduced Sasakian manifold? I am not found. Proof. Let B xi y tilde z equal 0 be on 2n plus 1 dimensional manifold, almost CFA manifolds M for any y w z in u w z in gm. Then we have equation. Yes. This equation using double question is B xy u. B xy u double question equation. Using double question equation, we obtain this equation, and using we have to double equation. Double equation is tilde z y w z. We get this equation. This equation shows that the manifold reduce a Komatsu manifold for like we found before it. Alpha plus 1 divides 1 minus n equals 0. On the other hand, from we have this equation. So M is a real space form with constant sectional curvature. Real space form conditions is R, X, Y, Z. This is constant C, yani constant. G, Y, W, Z, A minus G, W, Z, Y. Real space form conditions. New theorem. Let M be 2n plus 1 dimensional and almost CFA manifolds, then B xy p equals 0 if and only if M either reduce a Komatsu manifold or an Einstein manifold. This results like before found. This proof is assume that B xy p equals 0 for all y u double z in gm. Then we have equations. This using double question. Double question is B xy w. Double question is B xy y w. We obtain this equation. This equation putting u equal xi in, we get this equation. This not seen. This is p y w z. This is with help of equation. We have this equation. Putting these conditions is this tells us either reduce a Chemaso manifold or it is a Einstein manifold. The converse is obvious. These conditions B QCYS equals 0 if and only if M either reduce a Chemaso manifold or an Einstein manifold. Proof is it is proof. Finally, this is my reference. This one reference is my filed. My paper is basis reference 1. Janses and Van Heck almost contact structure and curvature tensor. This is their reference. Thank you so much for listening to me.
Thank you very much, sir, Dr. Yildirim, for your valuable and interesting talk. Now, I invite to Dr. Silpi Jain to ask the question.
Thank you, sir. And first of all, thank you so much, sir, for your innovative session. This is very fruitful for the research work also. And my questions to you, sir. Under which condition every two form is a curvature tensor? Under which condition every two form is a curvature tensor?
What is the atlas and chart?
Sonsuzluk şartı gibi bir şey mi var?
C, infinitive C. Every mertebe is differentiable.
Okay, sir. Thank you all participants. It is my privilege to propose the vote of thanks on behalf of Poornima College of Engineering. Honorable dignitaries and dear participants, we want to express our gratitude to Honorable keynote speaker who has spread his precious time for us and graced the international webinar with his presence. I extend our sincere thanks to Professor Dr. Mahesh Bundele for addressing the international webinar and constantly motivating us and inspiring us. So thank you all so much. We look forward to same in future.
Thank you very much, sir.